I'm Tammy Kolda, an applied mathematician, and this is Unlocking LaTeX Graphics. On this channel, I present tutorials on using TXE and PGFPlots. The videos on this channel are based on my book, Unlocking LaTeX Graphics, as well as some bonus material. In my ongoing series about slope fields, I'm going to show you today how to use something called a Quiver plot in PGFPlots, along with external data files to create a slope field. A quiver plot is a special type of plot in PGFPlots for showing a vector field. For each xy point, you can specify a vector with components u and v, and PGFPlots will draw an arrow from xy to x plus u and y plus v. I'll show you how to create a slope field using the PGFPlots quiver plot type. In this case, I'm using a Python script to compute the slope field data for various differential equations and write that data to text files. Then in PGFPlots, I'll read that data and use it to create the quiver plots. So let's get started. Before we jump into the code, let me briefly explain what a slope field is. A slope field is a way to visualize a differential equation of the form dy dx equals f of xy. I use the shorthand y dot to denote dy dx. At each point xy, we draw a short line segment whose slope is f of xy. This gives you a global picture of how solutions to that differential equation behave. If you were to place a solution curve on this picture, it would follow the directions of these line segments. The example here shows the slope field for y dot equals x minus y, which is the equation we'll code up first today. Let's zoom in on what's happening at a single point. At each grid point xy, we draw a line segment of a fixed length, which I'm calling len. And the slope of that segment is f of xy. Here I'm showing you a Python file. I'm going to generate the data that I need for the slope fields using a Python script. This script evaluates the derivative dy dx at every point on a grid for a given differential equation, and then it writes the results to a text file. This is not a fully LaTeX solution, and I'll cover how to do this entirely in LaTeX in a future episode. But this is actually a much simpler approach if you can generate your data externally using Python or MATLAB or whatever you prefer. The Python script is pretty straightforward. I've copied it up to the overleaf so that you can pull it down. You can't see it on overleaf. It doesn't know how to view .py files, but you can copy it down and then play with it on your own machine. For each differential equation, it evaluates whatever derivative I specify at every point on a grid. Then for each grid point, it computes a unit direction vector with components u and v based on that dy dx formula. And it writes those to a text file along with the x, y, and function values. The u and v components are what PGFPlots needs to draw the arrows. If you want to create your own slope field plots, you would just modify the Python script with your own differential equation and grid settings, run it, and upload the new data files. Let me show you the data file for our first example. The file has 5 columns, x, y, the function value f of xy, and the direction vector components u and v. This data is for the equation dy dx equals x minus y on a grid from -2 to 2. Now let's set up our document. I'm using the geometry package with 1-inch margins, parskip to eliminate paragraph indentation, and hyperref to link the author name back to this YouTube channel. The key packages are PGFPlots and PGFPlotsTable. We covered PGFPlotsTable in the last episode. We need it here to read data files and reuse them. In the PGFPlots set block, I'm doing a lot. I'm setting the compatibility to 1.18. You always need a compatibility statement. I'm using scale on the axis, and then setting the width and height of 15 centimeters. I want these plots to be big so we can see the slope field clearly. I set the axis lines to the middle so the axis crosses at the origin rather than forming a box. And I'm setting axis equal image to ensure that the x and y scales are the same, which is important for slope fields so the angles look correct. I set the x label and y label and various styles. I set enlarge limits to 0.1 to give a little bit of padding. I set the tick distance in both the x and y direction to be 1, and I append every plot command with ultra thick so that you can see the slope fields clearly. Let's start with our first example, the differential equation f of xy equals x minus y. Here I've plotted a few things. I'm defining a formula, dy dx equals x minus y. I'm just using that in the plot of the title. And then I'm going to use a pgfplotstable read to read in the data file that I want to display. I could just read in that table each time I do add plot, but this way we can reuse it. I'm calling the macro that holds that SF table. Inside the Axis environment, I'm setting the title using that formula, and I'm putting down one add plot command. And this is not actually what we're going to use in the end, but I just want to show you where the x, y coordinates are. So I created in Python an evenly spaced grid, and I'm plotting a black circle at every x, y value in the table. Notice I didn't specify that the x values and y values come from those columns in the table, because by default table reads the first column being x and the second column being y. Now let's add the actual Quiver plot on top of these points that I've drawn. The add plot line here specifies that we should plot things in blue. I'm specifying an arrow type for now, and I'm specifying a special thing called Quiver. And so I'm saying U picks up the U column from our table, and the V picks up the V column from the table. And when I compile that, at each XY point, we're going to have an arrow emanating out of that in the direction UV. You can see these arrows, but they're actually quite long. So we can scale them down by coming up to the axis options and adding quiver/scale arrows equals 0.25. This scales all the arrows to 25% of their original length. That looks much better. Now you can clearly see the slope at each point. These slope field lines are starting to take shape, but they are not centered on the XY points. We could try to shift things around by adjusting the X and Y values that we use as the starting point. But then the quiver scale arrows option wouldn't work as expected any longer. But think of what I've drawn so far as just half of the line segment. Now I'm going to add the other half in the opposite direction. This way the line segment will be centered on the XY point and the scale will work correctly since both halves are scaled the same way. The second add plot is almost identical to the first. The only difference is that I'm negating the U and the V. I'm also using orange so you can tell which half is which. Together, the blue and orange arrows form a line segment centered at the point. Now let's clean this up a little bit. Let me get rid of these dots. We don't need those at all. Then let me get rid of this arrowhead. Normally slope fields don't have arrows. And then finally, let me change this also to the same blue color so that everything looks the same. And there it is, a clean field for dy dx equals x minus y. You can see the slopes following the pattern of the equation. Along the x equals y diagonal here, we have 0 slopes. We have another place where the slopes are exactly 45 degrees. Let's try a more interesting equation now. I'm just going to replace these two lines and I'll get a new slope field. This one is sine of 2x plus y. I'm reusing the exact same structure but with a different formula and data file. The equation is dy dx equals sine of 2x plus y, and the data is in slope field 2.text. However, I need to adjust the scale since this data is on a larger grid. The x values go from -4 to 4 and the y values go from -2 to 2. So I'm going to change this quiver scale to 0.15. That looks much better. You can see the wave-like pattern from the sine term combined with the exponential growth from the y term. Observe in this case that even though the x and y limits are different, the scale of the axes is the same, so that 1 unit in the x direction is the same as 1 unit in the y direction. That is important for slope fields so that the angles of the lines are accurate. And this is accomplished by the axis equals image option here in the PGFplots set block. Let me show you a few more examples to demonstrate how versatile this approach is. Example 3 is dy dx equals sine of x times y. This one creates a beautiful pattern because the product of x and y inside the sine creates a lot of variation across the plane. Looks kind of geometric, like it might make a nice needlepoint pattern. Example 4 is dy dx equals exponential of x minus y. The exponent creates very steep slopes when x is much larger than y and nearly flat slopes when y is much larger than x. This example caused us numerical headaches in plain TXE in the prior episode. You can see what caused the problem here. Some of the slopes are nearly vertical, which means the u component is very small and the v component is very large. Python did a much better job of handling this than TXE did, which is why you generally don't want to use TXE for anything computational. The last example is dy dx equals 2 cosine of x divided by y. This one is interesting because the derivative is undefined when y equals 0. The Python script handles this by using a vertical line segment at these points. It gets a nan for the f of x, y, but then it checks for the nan and then sets the u and v values accordingly. I hope you enjoyed today's episode on creating slope fields with the Quiver plots option in PGFPlots. The Quiver option in add plot takes u and v direction components from a table to draw a line at each grid point. And we use the trick of negating u and v to draw arrows in both directions for a traditional slope field look centered on the xy coordinate. In this case, I'm using Python to generate slope field data. To create your own slope fields, just modify the Python script with your equation, run it, and upload the data file to Overleaf. In the next episode, I'll show you how to create slope fields entirely in LaTeX without needing to generate the data externally. I don't necessarily recommend that approach since it's a little bit more complex, but it is possible and can be useful for simple equations or if you want to keep everything in one place. I linked to the Overleaf document I created today in the show notes. If you found this helpful or interesting, please click like or subscribe. If you have TXE or PGFPlots questions, please post them in the comments. If you want to learn more, please check out the other videos. I also have a book, Unlocking LaTeX Graphics, available for purchase at major book retailers. Thanks for watching.